Hello all, good evening. Welcome back to my YouTube channel all about VLSI. Hope you're all doing good, right? So let us start today's session. So in this session we are going to start about we are going to discuss the continuation of building logic gates with the help of NOR gates. Okay, so in our previous session we have discussed it with NAND gates. So we have built the gates using NAND. Okay, now in this session we are going to build NOR gates. Sorry, we are going to build the logic gates with the help of NOR gates. Okay, so before starting the session, make sure that you have subscribed to our YouTube channel all about VLSI if you haven't. Okay, yeah. So let's start our session, and I hope my screen is visible and my voice is also audible. Yeah. So in our previous session, we have completed with the discussion of building basic logic gates with the help of NAND gates. We have built AND gate, OR gate, NOT gate, XOR gate. Up to XOR gate, we have seen how to build the gates. Now I have given you a simple task to build the XNOR gate using the NAND gates. To build the XNOR gate using the NAND gates, I hope you have done those. And let us see how to build a XNOR gate using the NAND gate. Okay, so simple. Here we have built a XOR gate, right? So we have built a XOR gate, and so this is a XOR gate, and we just add one more NOT gate to this XOR gate to make it as a XNOR gate. So we will make a NOT gate with the help of NAND gate. So how to make a NOT gate with the help of NAND gate? So this is how we are going to make a NOT gate with the help of NAND gate. So this will become a XNOR gate. That is, the equation will be equal to A bar B bar plus A B bar. That's it. So we are going to just add a simple NOT gate. So we should build that NOT gate with the help of the NAND gate only. Okay. So it will become a XNOR gate. Okay. That is about building NAND gate, building all the logic gates with the help of NAND gate. Now we will see how to build all the logic gates with the help of NOR gate. Okay, so how NOR gate is acting as a universal logic gate, that we will see now. So how to build a NOT gate using NOR gate? How to build NOT gate using NOR gate? So what is the functionality of a NOT gate? We already know. So how to make it? How to make a NOR gate work as a NOT gate? So we will simply short the two inputs. Okay, the same thing which we have done in the case of NAND gate, that only we are going to do in our NOR gate. Okay, so this is what we are going to do. Y is equal to A plus A bar, which will be equal to A bar. Okay, so our input is A, then output will be equal to A bar. That's it. So we are just simply going to short the inputs of a NOR gate to make it as a NOT gate. Okay, to make it as a NOT gate. So this is how we are going to build a NOT gate using a NOR gate. Now let us see how to build OR gate. How to build OR gate using NOR gate. OR gate using NOR gate. How to build a OR gate using NOR gate. Okay. So basically the equation for OR is Y is equal to A plus B. So this is the equation of OR gate. So this we have to achieve using a NOR gate. So what happens if we give two inputs A and B to our NOR gate? So let us see. So we will give two inputs to our NOR gate. Then if we apply A and B, then Y will be equal to A plus B bar. A plus B bar. Y is equal to A plus B bar. Now to remove this bar, we can apply it to a NOT gate. So how to build a NOT gate using NOR gate, that we have already seen in the previous slide. So this is how we are going to build a NOT gate using a NOR gate. So we will just simply build a NOR gate using the we will build a NOT gate using a NOR gate. Okay, by shorting the two inputs of the NOR gate. So it is a NOT gate. So finally we will get the output as Y is equal to A plus B. Okay, so this is how we are going to build a OR gate using NOR gates. Now let us see how to build AND gates using NOR gate. How to build AND using NOR gate. So the equation for AND gate is Y is equal to A dot B. The equation for our AND gate is nothing but y is equal to a dot b, we already know. But what we have, what we will get when we apply a and b to our NOR gate, if we apply a and b to our NOT gate, we will get the equation in terms of addition, that is y is equal to a plus b the whole bar. Okay, so we will modify this equation so that the equation will be in the form of addition. Okay, so what can we do? We will apply the double complement on both the terms, that is y is equal to a double bar dot b double bar, that is a double bar is equal to a and b double bar is also is equal to b. Now according to De Morgan's law, a bar dot b bar, which will be equal to a plus b the whole bar, so y will be equal to a bar plus b bar the whole bar, a bar plus b bar the whole bar. So we have got this equation a bar, okay, plus a bar plus b bar the whole bar. Okay, now how to implement this particular equation using NOR gate? Let's see now. Okay, this is bubble here. So how to implement a bar? So simply build a NOT gate using a NOR gate. So short the inputs, so it will become a NOT gate, a, it will become a bar, and this is b, it will become b bar. Okay, a bar and b bar. Now this a bar and b bar are applied to another NOR gate, so that it will become a bar plus b bar the whole bar, a bar plus b bar the whole bar. So this is nothing but a AND gate. So this is this total logic diagram is nothing but our AND gate. So this is how we are going to build a AND gate using NOR gates. So this is how we are going to build a AND gate using NOR gates. Now let us see how to build NAND gates using NOR gates. How to build NAND using NOR. So what is the equation of NAND? We know y is equal to a dot b the whole bar. We know y is equal to a dot b the whole bar. So according to De Morgan's law, we can solve this by a bar plus b bar, a bar plus b bar. So this a bar plus b bar can be further written as a bar plus b bar double bar. So if I apply double complement, then I will get a bar plus b bar that double bar. Okay, so this is what I am having. Okay, so this is what I am having. So I have converted this equation into a bar plus b bar the double bar. Okay, so this, if you observe, this a bar plus b bar the whole bar, this is nothing but the AND gate. This is nothing but our AND gate, which we have seen in our previous slide. A bar plus b bar the whole bar is our AND gate, and now we are complementing it further so that it will become a NAND gate. So for this same, we will consider the same logic diagram. So it will be like this. So NOR gate, we will apply a here and b here. So it is given to another NOR gate. Okay, and this is our a bar, b bar, a bar plus b bar the whole bar. This is our AND gate, and we will apply it, the output, to a NOT gate to become a NAND gate, So finally it will become a bar plus b bar the double bar, a bar plus b bar the double bar, which will be equal to a dot b the whole bar. Okay, so this is how we are going to build a NAND gate using NOR gates only. Okay, now let us see how to build XOR gates using NOR gate. How to build XOR gate using NOR gate. XOR using NOR gates. Okay, so we know the output of XOR gate is nothing but y is equal to a bar b plus a b bar. So this is the equation if a and b are the inputs of our XOR gate. Now this equation we can modify it as y is equal to a bar dot a plus a bar b plus a b bar plus b bar dot b. Okay, here we have added two zeros, plus 0 plus 0. 0 is nothing but 0 can be written as a bar dot a, which is equal to 0, and this 0 can be written as b bar dot b, which is equal to 0. So that is what I have written. And so from here we can take a bar common, so it will become y is equal to a bar. If I take common, it will be equal to a plus b, plus if I take b bar common, it will become a plus b. Okay, a bar into a plus b plus b bar into a plus b. Okay, now we can what we can do is I'm applying double complement to this a plus b term. Okay, I'm applying double complement to this a plus b term. Okay, just for simplification purpose we are performing all the steps. Okay, so a bar into a plus b double bar, that is nothing but a plus b only, and plus b bar into a plus b double bar. Okay, now what we can do is basically we are multiplying all the terms, and we will get a bar into a plus b the double bar and b bar into b plus b the double bar. So it will become a plus b bar the whole bar, and plus b plus a plus b bar the whole bar. Okay, so I'm rearranging it. Okay, that's it. So a plus a plus b the whole bar plus b plus a plus b the whole bar. Okay, so according now this can be further simplified as, so I'm applying double complement to the whole term. So it will become double complement a plus b bar the whole bar plus b plus a plus b bar the whole bar. That's it. So this is the term we are having. Now this term we are going to implement it in using NOR gates. The NOR gates. So how to implement this? So the first term is a plus b bar. This we have to implement. So here we have a and here we have b. We are applying it to a NOR gate. So I will get a plus b bar. Okay. So this a plus b bar, and we have one more term a plus b bar the whole bar. Okay. This how to implement this? I will apply here and here to a NOR gate. Okay. So this will become a plus b bar the whole bar. And similarly here another term we have b plus a plus b bar the whole bar. Okay. So I will apply here. NOR gate, I have b plus a plus b bar the whole bar. Okay. Now this two I will apply it to another NOR gate. So the equation becomes, so it is a NOR gate. So the equation here at the output becomes a plus b bar the whole bar plus b plus a plus b bar the whole bar. And finally the output is again given to a NOR gate. So I will draw it here again for more clarity. So it will here a NOR gate, and it is given to one more NOR gate. Here we will apply b. Here we are going to apply a, and this it is given to a NOR gate, and this output we have is a plus b the whole bar, okay, plus b plus a plus b the whole bar, I will write it here. So here we are having the output which is a plus b bar the whole bar plus b plus a plus b bar, okay, the whole bar. We have the bar for, okay, and this is further given to, which is acting as a NOT gate. So finally at the output what we will have, one more complement. So this is the XOR gate. This is the XOR gate using NOR gates. So how many NOR gates we have? So how many NOR gates are required to implement a XOR gate? So we need 1, 2, 3, 4, 5. We need 5 NOR gates to implement a XNOR gate. Okay, sorry, to implement a XOR gate, and we need 6 NOR gates to implement a XNOR gate. Okay, we need 6 NOR gates to implement a XNOR gate. So this is how we are going to implement all the logic gates with the help of NAND gates and NOR gates. We are going to implement all the logic gates with the help of NAND gates and NOR gates. So that's why these NAND gates and NOR gates are known as universal logic gates, because we can implement any gates with the help of this universal gates. So that's why these are called as universal logic gates. Okay, yeah. Now let us see one more concept. So from this we can come to a conclusion that, so this NOT gate, what is the alternate representation of this NOT gate? So if it is A and here A bar, the alternate representation of this NOT gate is bubble in front of at the input also. So these two are similar. So a NOT gate, okay, the bubble at the output which is equal to bubble at the input. So these two are same representations. Okay, so this is normal representation of NOR gate and this is alternate representation of NOT gate. This is normal representation of NOT gate and this is alternate representation of NOT gate. And this is about NOT gate. And coming to AND gate, so this is the normal representation of AND gate. If the inputs A and B are the inputs and Y is equal to A dot B. So this is the normal representation of AND gate, and this is the alternate representation of AND gate. A bar plus B bar the whole bar, which is nothing but AB. Okay, so this is, okay, bubbled 2 input NOR gate. Okay, bubbled input NOR gate. Okay, AND gate can be represented as bubbled input NOR gate. So this is also alternate representation of AND gate. Bubbled input NOR gate is alternate representation of AND gate. Now let us see for OR gate. So we have our OR gate like this. So it can be represented as, if A and B are our inputs, that is A plus B. So the alternate representation of this OR gate can be bubbled input NAND gate. A, B, A bar dot B bar the whole bar, which is nothing but A plus B. So this is bubbled input NAND gate. So this is the alternate representation of our AND gate. What is the alternate representation of AND gate? It is bubbled input NOR gate, whereas the alternate representation of OR gate is bubbled input NAND gate. Okay, now let us see what is the alternate representation of NAND gate. So this is our NAND gate. So this is a normal representation of NAND gate with inputs A and B and output Y is equal to A dot B bar. Okay, and the alternate representation of NAND gate is bubbled input OR gate. Bubbled input OR gate. Bubble means we are basically negating the inputs A bar plus B bar. bubble at the input, which means we are negating the inputs. Okay, here A means it will become A bar to the A bar as the input and B bar as the input over OR gate, so it will become NAND gate. So this is the alternate representation of NAND gate. What is the alternate representation of NAND gate? Which is bubbled input OR gate. And coming to NOR gate, so this is our NOR gate with inputs A and B and output Y is equal to A plus B, the bar. So it is nothing but bubbled input AND gate. Bubbled input AND gate. A and B, Y is equal to A bar dot B bar, which is nothing but A plus B bar. A plus B bar. Okay, so this is bubbled input AND gate. So this is a bubbled input AND gate. So the alternate representation of NOR gate is bubbled input AND gate. So these are the alternate representations of our standard logic gates: AND gate, NOT gate, OR gate, NAND gate, and NOR gate. So this is how we are going to represent our alternate representations of normal logic gates. Right. So that's all for this session. So if you like this video, please like, share, and subscribe to our YouTube channel, All About VLSI. Okay. Thank you.